Okay, last bit of proof. We're looking at graphical ways of solving inequalities, I guess we could call it. Now, these sorts of inequalities, well, inequation would be more correct, I suppose. If we had to solve this type of inequation, I could draw the graph, so x squared over x plus 2. Well, there's the two parts. So the red one obviously is x squared, the blue line is x plus 2. So if I was unsure what this looked like, I could go, well, hang on. I know there's going to be a vertical asymptote there because bottom of the fraction can't equal 0. Then I could work out where's it positive and where's it negative. So on the left-hand side of that, I've got a negative times a positive, which is negative, then go positive, positive, so I know where it goes. Looks like we've got an x-intercept at 0, do we? Yeah, we do. Okay. And that happens to be the y-intercept as well. What else can we work out? We can work out the asymptote. So if I did a polynomial division on that, we end up with x minus 2 minus 4 and x plus 2. So we have an oblique asymptote at y equals x minus 2. Let's draw that in. What else do we need? Well, that's about it. We can get a rough sketch from there anyway. Good enough for what we've got to do. Let me get rid of those construction lines. There's our graph. Okay. We want to know when is that graph less than or equal to 1. So if I draw in the horizontal line 1, we're basically saying when is the blue curve below the red line. So I'm going to have to find those points of intersection, the red line and the blue curve. So that's just a matter of solving them. And we get x equals 2 or minus 1. Unless, of course, you had an incredibly accurate graph like I do here, and you could just read it off. But I mean, I got lucky, I suppose, because they happen to be integer solutions. If they weren't, then I'd have a problem. Okay, so when are we below the red line? Well, we can clearly see on the left-hand side of our vertical asymptote, we're always below the red line. So x is less than minus 2, but also in between those 2 points of intersection, we're also below the red line. Now, I'm not suggesting that's the best way of going and solving that problem, but it's certainly a way we could do it. And if we happen to have that graph already, it might be quicker. So that's probably the first sort of problem with inequations, inequalities, where we use graphs to solve the problem. Let's look at ones we're more interested in though, for extension 2. So they've asked us to consider the graph y as the square root of x. So parabola on the side, top half of the parabola. And they've drawn in some of the, what we would call the outer rectangles there. Now, the first thing they've asked us to do is to show that that graph is always increasing. Now, clearly, I mean, we can see it is, but that's not good enough for a proof to say, oh, well, I can see it is, therefore it is. So what have I done? We know we can use the first derivative to work out when the curve's increasing. So the first derivative here is 1 on 2 root x, and that's always going to be greater than 0. So I know the derivative is greater than 0 for x is greater than 0. Now, whether I need to do the next bit or not, I don't know. I've often thought, is this a waste of time? Well, what's happening at 0 itself? At x equals 0, y is 0. And when x is greater than 0, y is greater than 0. And we also know it's increasing, so it's always going above 0 from the initial point. That's probably overkill, to be honest. I think the derivative just being greater than 0, I think is good enough. So yes, that curve is always increasing. Hence show that the sum, and that turns out to be, if you go back to the diagram, the sum of all those rectangles. Hence show that sum is greater than or equal to the integral, which turns out to be 2/3 n root n. Okay, so I think I'll use my graph again. There it is. So as the square root of x is increasing, now it's interesting they say that, because if you think about it, it's not so much that the square root of x is increasing, but it's more to the point that it's concave down. See, if it was increasing and concave up, how would those rectangles go? Would they also be greater than? Think about it. Draw something that's concave up. Yes, someone said it. Yeah, you're thinking of using trapeziums. It would be true. Well, in this case, if we were using trapeziums, it wouldn't be greater than. But we're using rectangles. So actually, it doesn't matter the concavity. I led you into a trap there. All right. So the first part is why they then said, yeah, show that's always increasing. For this one, the key is it's always increasing. So the area of those outer rectangles will always be greater than or equal to the area under a curve. Thus, we know the first part of that inequality is true. but they also want us to work out the value. So let's go and do that integration. And when we integrate root x, well, I've jumped straight to it. I mean, it's one of those common ones we do, but you know, it's x to the power of a half, add 1 to the power over the power. So I know I'm going to get 2/3 x root x. And sub that here, the n in, and of course 0 is just 0, and we get our result, 2/3 n root n. Okay, so we've got the first part. Now they want us to use induction, that same series, but show it's less than or equal to 4n plus 3 on 6 root n. So we can use induction for this one. All right, well, let's prove it's true for the first case. Right-hand side is 7/6. And yes, 1 is less than 7/6. So, yep, our base case it works for. I'm going to assume it's true for k, where k is a positive integer. So, subbing k. Now we want to prove it's true for k plus 1. K plus 1. So that's what I'm attempting to prove. Again, I'm using the idea of moving everything to the left-hand side. I'm going to show this is always negative. It's a series type, so I'll rewrite it so I can get the assumption in. There's the sum to k plus, I did 2 steps in one, didn't I? Yeah. I read the second last root k there, but then I've added the root k plus 1s together as well. Okay. Repeat that. So this was the initial statement that I'm trying to show is negative. I put in the term before root k plus 1, root k, but also I've added these 2 root k plus 1 terms together to get 4k plus 1 on 6 root k plus 1. So I did 2 things in one step. Sub the assumption in. All right, remember we're trying to show this is always negative. Well, let's write it all as one fraction. But the other thing I've done with the first one is write that as an entire surd. So I've got 4k plus 3 all squared, lots of k. I haven't done it to the second one though. And I guess the reason is I could have done it with the second one and not the first one. That would have been equally valid to do, but I'm trying to get the surd the same. So the first one, if I expand it out, becomes root 16 at k cubed, 24k squared, and 9k. Remember, I'm trying to get something times k plus 1. It's close. If I divide it by k plus 1, it works, but I get a remainder of minus 1. But because I'm dealing with an inequality and not an equation, that minus 1 I can now get rid of. Because I can say this line here has to be less than the line underneath it. Because effectively, underneath the surd, I've added 1, so I've made it bigger. So this line has to be less than the one underneath. I've now got that factor of k plus 1 that I was looking for. And 16k squared plus 8k plus 1 is 4k plus 1 all squared. That's nice, because now I can simplify that surd. And that's equal to 0. So therefore, that is less than or equal to 0. That's what I was trying to prove. Hence true for k plus 1 if it's also true for k, etc, etc, etc. Okay. Use part B and C now to estimate root 1 plus root 2 up to root 10,000, but to the nearest 100. I can now sandwich the sum, because I've shown it's greater than something and also less than something. Therefore, it must be between those two things. If I sub in n equals 10,000, let's work out what those two endpoints or end expressions are to the nearest 100. And something lovely happened. They both turn out to be 666,700. So if it's between 666,700 and 666,700, it's fair enough to deduce that, well, that sum must equal 666,700 to the nearest 100. I'm going to prove that x is always greater than sine x. Well, if x is positive. Let's draw the graph. That's going to be y equals x right there. And there's y equals sine x. Again, you can't just look at the picture and go, oh look, the line's above the curve. We know function x is equal to x. So its derivative is 1. So that blue line there has a slope of 1. Now, the trig curve differentiates sine. Whilst we haven't seen this yet, you're going to have to just believe me here. We'll see it soon. But differentiate sine and you actually get cosine. Between 0 and pi on 2. Right, so between 0 and pi on 2, cosine of x is less than 1. So the slope of the sine curve is less than the slope of the line. So the line must be increasing quicker. So y equals x will increase faster than y equals sine x, but they both start at 0. Now what about after pi on 2? Well, again, I suppose you could look at it and go, oh, clearly it's above. So for x is greater than pi on 2, we know sine x is always less than or equal to 1, but x, of course, is going to be bigger than pi on 2, and pi on 2 is bigger than 1, so x must be greater than sine x. Thus, x is greater than sine x for all x greater than 0.